Welcome to CHEM103 for Wednesday, I've lost the days. I think it's the 30th of March. I should really know what day it is. Apologies for starting a little bit late. I'm having some problems with my UWO laptop, but I seem to have sound, so it's all good. You can see me, so we can get this lecture going for today. Let me just share my... So you are familiar with this. We are here. So I want to start today with talking about a couple of things that caught my attention that have some relevance with engineering and some relevance with what we've been talking about. In particular, this paper, it came out a couple of years ago, and it talks about a mobile robotic chemistry, and the analysis that it's doing, if you read where it says on the red arrows, it says they're using a mobile robot to search for improved photocatalyst for hydrogen production from water. So hydrogen, so water is a source for getting hydrogen, and then photocatalyst is something that is added to this process to speed up the rate of production. So the conventional way of doing this would be to look at the sample space and then do a whole bunch of experiments and possibly examine which are the likely candidates. However, in this case, in this paper in Nature, what they're actually doing is they're using a robot. And if you look at the sentence underneath the red arrows, it says the robot operated autonomously over 8 days. And that is probably 8 days as in 24/7, whereas most people, if they work in the lab, they will not work 24/7. The nice thing about this as well is you can, if you use a robot, then you can also go for a brute force approach. And with the brute force approach, I mean, you just examine every single possibility because you have a robot, there's no human involved, you can just get the robot to do the work. And this is something that is coming up more and more, and obviously robotics is a, I think it's called a field of engineering. I have done a little bit of work with Professor Gursel Alizi and Jeff Spinks on the soft robotics program, where we use softer materials to make robotic devices that were mainly powered by air. But we also made soft grippers that we could use, and all of that was based on some additive manufacturing technologies. So if we actually examine what this is doing, so it does say in that abstract that is autonomously, that's obviously only when the system is in operation. And here you can see this picture. So this is a mobile platform that can run. It's got some sample storage space. It's almost like a motorized trolley. And then the key thing of this is obviously this nicely constructed robotic arm. And the way that this has been done, it would have a human to set up obviously all the lab experience that, or all the lab setup that you see here. And in this sequence of events here, you can also see a map of the lab where they've got the robot. There's some inputs. There is a GC, which would be a gas chromatographer. There are some liquids. A sonicator is really like a really high frequency mixing instrument. And then what would happen is this robot would pick up some of the samples. It would also then load empty samples into, I think this might be a gas chromatographer, or this could be the gas chromatographer. This might actually be a setup system. Then it's loading samples, and then afterwards, it's also storing the completed experiments. And then what you can do, excuse me, and these are obviously from, I've taken these from this reference of the Nature article. You can then look at, you know, what happens, what is your output? So in terms of hydrogen, here is a sequence of the days of a timeline. And then here at the bottom is the number of experiments that were performed. And then the black dots here are probably on each of the days a number of the experiments were done as control, so that if they were looking for this new improved photocatalyst, they would then, the robotic system would then also do the controls. And you can see that the controls aren't absolutely always the same, which is what happens a lot. And then they can do these different type of what is called experimental space. You know, obviously there's some really good output here when you get to some of these later experiments. And then in this so-called spider diagram, you see these different types of photocatalysts that are being used. So there's simple ones such as sodium chloride, sodium hydroxide, sodium silicon something. There is an L-cysteine, where L refers to it's one part of the molecule that has a particular orientation. The way to think about this, if you haven't come across these terms, there could also be an R-cysteine, and that literally means left and right. So these are molecules that have the same molecular structure, but they are similar to the way that your left hand and your right hand are similar. So our left and our right hand are the same, but they're mirror images of each other. So with molecules, you can also have, when you synthesize a particular molecule, you can end up with a mixture of molecules that look the same, but are mirror images of itself. And they can also have different properties. Anyway, I'm digressing. The SDS here is sodium dodecyl sulfate, which is a very well-known surfactant that you'll find in shower gels and washing up liquid and detergents. Rhodamine B, I think, is some form of coloring agent. Acid red, same as methylene blue, but they also have some catalyst. PVP is a polymer. It stands for polyvinyl pyrrolidone. I think it's a water-soluble polymer. And then it looks like from all of this phase space arrangement that there seems to be good performance happening with this L-cysteine. Anyway, so if you're interested in this, the details can be found in this paper. Now, the main findings of this paper were that through the use of this robot, they could do loads and loads and loads of experiments. In actual fact, they did 688 experiments in 8 days. And to use the words that they have in this paper, if you were to do this equivalent of manual experiments, then you generally need about 500 days of human research time, where I believe 500 days, I don't know if that means 8 hours of a working day or 7 hours of a working day, or whether that actually means 24 hours. I have to read the paper again. In contrast, where the advance comes in this case is that the 1,000 robot experiments only require this setup time, and then obviously at the end to have a look through the data, and that's about half a day of human researcher time. It probably, and that's not, I think, is discussed in the article, but if you do have one of these robotic labs, that when that robot is in operation, I'm not entirely sure if it's actually a robot or a cobot. So cobot, and you probably all are much more familiar with this than I am. A cobot is a robot that can work in a cohabitation next to humans. I don't know if that actually says that they completely empty the lab and just let the robot do the work by or carry out the experiments. Anyway, I found this very interesting. I think that's a very interesting area where engineering and chemistry have very good overlap, where each of the different fields could use their own complementary expertise. So we've talked a lot about the male scientist. Here is an article that I was reading in a magazine that I get because I'm connected to the Royal Society, or not connected, I pay the Royal Society of Chemistry for a subscription. It's called Chemistry World. It was in the January edition on page 33, and it talks about June Lindsay, so a female scientist, and the tagline has, "It's another forgotten woman of DNA." So I've looked at this article, and it's interesting. Oh, what's happening there? It's interesting because they talk about different molecular structures. The other thing that is very interesting is that this is a female scientist, and you can even see here these different types of structure. So who was she? She was actually born Broomhead, that was her maiden name, in Doncaster, which is in the northeastern part of England in the United Kingdom of Great Britain and Northern Ireland. It's actually in the county of Yorkshire, I believe. She only passed away last year. She went to Cambridge, and she's really known for crystallography, where she actually resolved the structure of adenine and guanine, if I pronounce that correctly, which is really important for the structure of DNA. So here is a 1948 paper that she's obviously now known as Lindsay, but she was then Broomhead. The other thing that I find very interesting in this is that it is a single author paper. That's pretty rare these days. You always would have multiple people as part of your team. Usually some person designs the experiment, and then a few other people would then carry out the work. And what she actually did is she used X-ray analysis. She used some mathematical method, which is the two-dimensional Fourier method. Bear in mind, this is before any sort of computational power, so she would have had to do her Fourier transfer using books and tables probably. And what she did is she established the crystal structure and then goes on to describe what the crystal structure is. She also talks about hydrogen bonds, which is one of the bonds that we've been talking about, that actually link molecules into water molecules, that actually allow some of these structures to have that particular type of arrangement. You know, we talked about water, you've done a workshop. It also talks about the short van der Waals contacts, which again are some of these forces and interactions that occur in molecule. And then she says where they roughly lie. So here is where she proposes the structure. If we examine that, you can see we've got a nitrogen coupled to carbons. There's some double bonds in there. There's an NH2 group. We've got lots of hydrogen. So there's a lot of potential in these groups to participate in hydrogen bonding, but also obviously the van der Waals and London forces. And then over here, you know, there's this is the guanine, which has, you know, similar type of arrangement. Again, oxygens, nitrogens, hydrogens. So a lot of opportunities to actually become involved in hydrogen bonding. So why was her work so important? So according to this book, and I didn't read this book, I took the quote from this book that appeared in the article, and it actually says there, and I quote, "The penny dropped when Watson consulted Lindsay's thesis," end quote. So Watson, in this case, is James Watson, from the person who was one of the people that got the shared Nobel Prize in 1962 for the solving the chemical structure of DNA. And here's one of these diagrams that we've used before from the compound interest. And here you can see the structures of adenine and guanine coming in to the structure of the DNA. And in particular here, if you look at what holds DNA strands together, then you've got this adenine with, that is thymine, I believe, and then guanine with cytosine. So it's these, you can see here, these dotted lines. I don't know if that's visible, but you can see it in the notes. So you got these dotted lines where we've got this hydrogen bonding that really keeps this particular type of structure together. And they're also color coded here. So yellow is thymine, that's interacting with the adenine, and then you can see the colors as it go along. And that gives us that particular type of the chemical structure of DNA. So according to this article, you know, it was only when this person, James Watson, looked at Lindsay's or Miss Broomhead's thesis and then figured out that there was, you know, that's where the structure came in, and that would help them to solve this DNA. The interesting thing about the DNA paper is how short it is. This is the 1953 article that appeared in the journal Nature that simply has the title, Molecular Structure of Nucleic Acid, a structure for DNA. So now we take this for granted. So if you look, it is barely a page long. And this is obviously a very important paper, because this is what established the structure of DNA. And it actually starts with, we wish to suggest structure for the, and my eyes aren't that good, so I can't even see what that says, for the something, or for the salts of deoxyribonucleic of DNA. And you can see they only have 1, 2, 3, 4, 5, 6 references, and then there's 2 authors there from the same laboratory. Well, it's actually the Cavendish laboratory from the University of Cambridge in the UK. This is, there are not that many words in there, and this is obviously a very important paper that has been cited many, many times. So if you, let me go back a bit. So if you remember the post-lab quiz for laboratory 1, there was an issue there with the one of the questions where the question said you need to give your answer in significant figures, yet the way I had set it up, it was actually looking for decimal whatever it's called. But anyway, so everybody got one of the questions right. So I did updated the marks, but then uploaded earlier on this week a version that still hadn't had corrected. So if that sounds a little bit puzzled, just go to Moodle, and if you downloaded it and it didn't say updated 29th of March 2020, then you should probably click on it and you can actually see the mark that you will receive if you answered question 1 correctly with the significant figures. And linked to that, I got a question that talked about apparently some of you are getting confused with the results that are out on Moodle. So that's why I've just put this email out here that says, this particular person, de-identified, of course, I received a 5.56 for my working and was curious where I lost the marks. So this person showed Dr. Holly Warren, her workshop quick quiz, and said, there weren't any problems with it that much. So just to clarify, there are no marks available yet for workshop 1. I'm still waiting. I'm doing some, people are doing a makeup task who were unable to complete it. Once that's done, I need to do a couple of more checks, some manual checks, and then I will release the results. So what is out there at the moment are the marks for the post-lab 1 quiz, and some of them are incorrect due to that question 1. So if I go back a slide, so to get your correct score for post-lab 1 quiz, just download. There's a question on the chat. I've got 2 different marks. Which one will be counted? So 2 marks. So 2 marks means you did face-to-face and online. So in any case, I will take the higher mark. So if for some reason you did both the online post lab quiz 1 and the face-to-face one, I'll take the higher mark. You're welcome. So what's coming up, or what's actually happening? So workshop 2 is currently in progress. All the face-to-face classes and the live stream and the self-paced activity is still out there. You are probably at the moment doing your quick quizzes. Then I'll switch tomorrow. I believe it's tomorrow. I'll switch it over to the peer assessment task. So what we're doing today is obviously some of the last bits of the lecture material, because next week what we'll be doing is we will be going through some questions similar to what you can expect at the mid-session test, because that's coming up in week 7. So, and I'll have a couple of slides to explain a few more things about the mid-session test. There we are. So just to clarify, the mid-session test will be completely online. It is going to be online via Moodle, I would say. It is not timed. It's going to be open for 5 days. And it also looks that I can't spell. It should be 15th of April, which is Good Friday, I'm aware of. But I'll open it on probably on Monday the 11th. I might even open it earlier. I just haven't put it together. It is also open book, which means you can use whatever resources you can find. It's not timed. Let me stress that again. It is not timed, and it's worth about 20% of your total mark. Questions in there will be similar to what we will be discussing. There are some questions about how many questions is our final in the same. So let me address that. So so probably 20 questions, but I haven't written it yet. Midterm yet, but that's what it will be, roughly 20 questions. And as discussed in lectures and on Moodle information, yes, the final, the end of term test will be over multiple days and open book. I don't really believe in testing how good your memory is, because if I do something in real life, I look stuff up as well. So that's why most of my things are open book, because you can write questions in a way that require you to look at the material and then think about your answers. You're welcome. There's a question there, you should convince the other lecturers. Well, when I was a student, that was, or when I did engineering as an undergrad in the Netherlands, most of my assessments were actually open book, you know, and that in those days that was before the internet was widespread, which is probably going to show my age, but that actually was open book. So I distinctively remember taking an exam for a subject I truly was not, let me choose my words carefully here, wasn't my favorite subject, which involved organic chemistry, because we had to do that as engineers. And it was open book. We could bring whatever we wanted. So in those days, you would have a big bag with you full of books and notes and papers. And you would do the exam. And similarly, when I went to Ireland, a lot of the exams that we did there were open book. And now that I think about it, when I was in America, I did a similar thing there. So open book means you gotta think about some of the questions. There'll obviously be questions in there that are relatively simple to, actually, let me just rephrase that. If you've followed the lectures and you understand most of the materials, then I'm expecting that everybody can pass not just this mid-session test, but the entire subject. I teach so that people get opportunities to pass. I do not teach for you to fail. Anyway, I am digressing. Oh, there it is. That was the question that somebody had. How many questions? So I've obviously already written this. So it is 20 questions. And just to clarify, it's going to be based on materials covered in weeks 1 to 6. So 6 are the problems that we're going to work through. And as I just said, I'm going to repeat myself. I am expecting that you all should be able to pass this. Well, what else have I got here? Oh yes, this is something else. We talked about exothermic and endothermic reactions. So this is another article. For some reason, I was reading this. It sort of caught my attention because it used the words endothermic and exothermic reactions. At the moment where I'm sitting, it's a rare sight, but the sun is out in the sky. As you can feel, if you go and stand in the sun, you can feel the heat. So there's heat coming off the sun, which means it's an exothermic process. It's releasing heat. I'm not a big expert on how it actually works, but what I can find is you need the element hydrogen, and then when you get a combination of hydrogens and protons and neutrons coming together in a process that is called nuclear fusion, you then end up that some of these hydrogens can be converted into helium, and as part of that process, energy is released. And that's why the big ball in the sky, or in this nice graphic here, gives us nice warmth. And you can look up this article in there. So to dig in a little bit deeper as to what happens, and I took this from this reference here at the bottom from America. So exothermic process is really where you get some of these hydrogens that combining to what is called deuterium, I think, which is where you've got, so it's H2. In that particular process, you get some energy release. This process can collide again with some of these protons from hydrogen, and you get a helium form, some form of helium. Again, you get a release of energy. That can form to something that is unstable as in beryllium, which can then go into helium. At each of these paths, if you look, so we've got a reaction. There's an arrow that says these reactants turn into products, but we also have this other symbol here. We've talked about this before, where you can have these little triangles above that tell you that you're putting in heat, but in this case, you can see this other arrow here. There's a lot of energy being released. So the reason why the actual energy in this process is exothermic is that the binding energy is, so the energy required to go from H1 to H2 to helium-3 to helium-4 is that the binding energy required for this. So the energy, we talked about this before, if you want to make something, if you want to make new bonds or put things together or change stuff, you gotta usually have an energy that is in there to bind something together. That costs energy. In this case, so to go combine these two protons and combine them into H, then cost us energy, but we're also getting energy. And in this case, because the binding energy is less than the energy that is released, you get a positive effect in energy. So there's more energy coming out of this, which means that the burning of the sun, or not the burning of the sun, the way that the sun gives us light, that process that is happening there is exothermic. Now, apparently, and I've taken this from this link here at the bottom, so this is called the fusion process. This fusion process will continue to go until all the hydrogen is used up. If I go back to the start of this, I can actually show you what we're talking about here. So the title of this article was How Elements Are Made Beyond the Star. So we're talking about processes that are occurring out in our universe. So the sun is obviously converting hydrogen into helium, but apparently if this keeps going, this process, then you get larger and larger and larger elements being formed. So you can get lithium, beryllium, boron, carbon, nitrogen, and there's different types of processes. Eventually what's going to happen is when you get to the stage where iron is being formed, so iron is element number 26, that's when, if you want to then make something larger than iron, because remember, if you want to go, let's say, from magnesium to iron, you got to add something to it. That requires a binding energy, either in the protons or whatever is being added to that. So that costs energy. At some particular point with iron, the binding energy becomes larger. So it's becoming harder and harder and harder to increase the size due to these collisions that are happening in fusion. At that particular point, the binding energy is more costly than the energy that you get out of that. And then you switch from an exothermic process to an endothermic process. So rather than being energy released, if we want to go beyond iron, then you got to put energy into it. And that, by the way, that energy putting into it is also what they're doing in these colliders. So they're adding energy into systems to create new elements. But that obviously costs energy. If that happens in our sun, then the sun will stop shining. And there's actually no exothermic energy coming in. It's only endothermic. The sun is actually going to end quite differently, but you can use Google or whatever search engine that you are using to have a look at what that process actually is. So in essence, this is actually a bit more physics than chemistry, and I'm not an expert in this area, but the key thing that you should take away, if you want to go from hydrogen to helium, you got to add something to your hydrogen, and that costs energy. But in the same process, if you do that, due to these collisions, you also get an energy released. And as long as the energy released is larger than the energy it costs to increase the mass, you're going to have an exothermic process. When that switches, that's when we go to endothermic. So this is another example of exothermic and endothermic processes. And you can use the link there to get an idea of if you want to delve deeper into this. Okay, so I've taken about 35 minutes to talk about some other stuff. So what I wanted to get at, and I'm going to finish this first lecture this morning at about 20 past 10 in about 15 minutes, and then we continue this afternoon to finish the rest of the material. So this is about, in the book, this is chapter 19, and it deals with chemical thermodynamics. The key learning objectives of this is there's a whole lot of terminology here. So I'd like you to be familiar with the second law of thermodynamics, which deals with disorder, and particularly this phrase entropy, which can be a very confusing topic. And then eventually I'd also like you to be familiar with the third law of thermodynamics. And then in all of these, we can do some calculations in terms of entropy. There's another phrase here, the Gibbs free energy. In all of these comes our stoichiometry comes back. So once we know what the reaction is, then we can use stoichiometry again to calculate entropy changes, and also this free energy. The free energy can also help us to understand how different reactions are occurring. So you might have seen my video on thermochemistry, which is which is something I really enjoy. Probably thermodynamics is part of that same thing, and it's really something I spent a lot of time on when I was an engineering student at the University of Twente in the Netherlands, while I was doing my PhD in Ireland, and when I had my first lecturing job in Dallas in Texas. And this is a book here. I recently had a consultation, and I think I brought this book out. It's not a very big book, but I used to teach this book, and I also used this in some of my research. It really deals with modern statistical mechanics. So statistical mechanics is another way of saying thermodynamics. So it all involves a lot of statistics, involves a lot of equations and a lot of thermodynamics. So really thinking how processes are driven. Are they energy driven? Are they driven by changes in entropy? So there's whole different types of things, and all of these things can come back into understanding what goes on in the world around us, even surfing, I should add. So just to quickly recap, the first law of thermodynamics tells us that the total energy of the universe is really not changing, because we cannot create energy and we cannot destroy energy. So the total energy is a constant value. We can just transfer. I've told you, I've given you my favorite example, which involves surfing, where you convert wave energy and potential energy into speed, power, and flow, and you can also convert that into throwing off spray off the back of a wave. And this is really what we went through this picture last week, where we have, in this case, Dylan Parisi from Ferrul from DP Shapes, and you can see him dropping down into the wave. He's doing his bottom turn. He's converting the potential energy, the wave energy, the push, and then he's going to transition into a cutback. While he's doing the cutback, he's going to use and not lose some of that energy, but transfer some of that energy in throwing spray. So the key point here is that we can transfer from what we would call a system, which is something that we defined last week as well, to the surroundings. So we can call the surfboard and the surfer our system. We can call everything else the surroundings, or we can call the surfer, the surfboard, and the wave our system, and then we can do this energy transfer. So the other bit we talked about last week was enthalpy, and we really went through this, and you would have seen that enthalpy can be thought of as long as we work at constant pressure, that we really, enthalpy is really equivalent to heat. Entropy is another term that I would like to introduce, which is a measure of randomness in the system. So depending on other people would say it's a measure of the chaos. You know, how random is something? Normally, if we would sit in a lecture theater, I would point to the way that everybody is sitting, and I would say, well, the way you have been sitting here is a random arrangement. There are a number of seats available, and you could have organized yourself in many different ways by each selecting the seat that you come into. So it's really a random arrangement rather than a structured arrangement. That's why this big dice is here. So both of these concepts, so enthalpy and entropy, help us to figure out whether a reaction is going to occur spontaneous. So will the reaction occur? Or if it's not spontaneous, then that obviously means we would have to do something to the reaction in order to make it proceed. But entropy is something that we can use to think about how, if a reaction can occur. Anyway, so it is a difficult concept to understand, and we only have 2 lectures to look at it. So the way I sometimes think about entropy is, if you want to think of how entropy works, everybody, or not everybody, but if you go and look at your dishwasher, in your dishwasher, you have all these racks available where you can put glasses, you can put plates, you can even put spatulas there, or whatever you think, right? So if you would ask 10 random people, they would all stack this particular drawer. If you give them the same amount of dishes to stack, they may all stack this differently. I know in my household, where my 16-year-old son will stack it different than my 5-year-old daughter, my wife will stack it differently from me. That is randomness. That is really a very good example of entropy, because entropy is a form of randomness. It's not a prescribed process that will happen. So if we now couple this to spontaneous, or not couple this, but let's just talk a little bit about spontaneous. a spontaneous process is really something that you do without you having to do any trigger in it. The other bit that is important for spontaneous is usually if you have such a process, and the most example, you can do this at home as well if you're interested in eggs or you want to crack some eggs. If you have an egg and you have 2 eggs in your hand and you hold them above a table, so there is already some potential energy in here. If you drop them, if you release the eggs, then why is that going back up? That's not what I wanted to show. Then what will happen is, as soon as you release this, there'll be some gravity come into play. The egg will fall and will crack. And this is an example of a spontaneous process. The reverse, the egg will not reassemble back into your hand again. So spontaneous means it's generally going in one direction, but it's not possible to do this in the reverse direction. Now, there's two things that are important to think about. Spontaneous doesn't necessarily mean fast. You can have reactions that are really fast that are spontaneous, and you can have reactions that are really slow that are spontaneous. You should also not confuse non-spontaneous with impossible. That's the comment that I made before. Just because something doesn't happen spontaneous in the current state, you can actually add something to it. You could put some energy into it, and that could make a reaction spontaneous where it normally wouldn't be. There's a question, decay be a spontaneous process? So yes. I'm doing this to the wrong one. There's a message there. Yes. Oh, let's try that. So me being me and being really cheesy, I no longer drive a Hilux, I drive a different car now, but I tested the egg example for myself. So if we want to talk about a spontaneous reaction, you can check that if you take a Hilux and an egg and you drive the Hilux over the egg, then the forward reaction is spontaneous. Right? I drive over the egg cracks, and then my dogs came out and ate the egg. But if I reverse, so if I apply the same mechanical energy in reverse as that I did forward, then the egg doesn't normally form again. So it is a spontaneous reaction, but it's not, the backward reaction is not, and this is a very cheesy example. So let's look at some other ones. So if we want to do things that are spontaneous, so we can change, and this is what I said before about energy. So you can use temperature and pressure. So temperature, you can also think about energy. If we take ice and you get your ice out of the freezer, or you have ice in a nice refreshing drink, if the temperature is above 0 degrees centigrade, eventually all your ice will melt and will turn into liquid water. That indicates that this process is spontaneous. If I would have the reverse now, so here is, we put energy into this. If we now take energy out of this system, so if we would put a liquid into the freezer, then eventually all our water will spontaneous over time reverse and turn into ice. There's a question there. What the egg wouldn't be cooked. So yes, I'm applying mechanical energy to the egg. So applying, and it cracks. Applying the reverse mechanical energy, so to say, does not uncrack the egg. Could you give an example of a non-spontaneous well, any sort of non-spontaneous process is, let me just go back to see what I said here. Previous, can I go back? No, it's not letting me go back. I'm going the wrong way. So actually the egg are really good examples of spontaneous and non-spontaneous process. So non-spontaneous, think about egg in the pan. It will not crack without you doing something to it. Another example would be, think about a match. It is non-spontaneous, but the match will burn if you add type energy to it. Yeah, does that make sense? Also, melting of ice is non-spontaneous if it is in a freezer, but spontaneous in the oven. Okay, this will be, where are we now? So we're at the spontaneous. So let me do this go through this last slide before I stop, and then we continue next week, which talks about reversible and irreversible processes. So let's talk about a reversible process. It's a system that can go to its original state by exactly reversing the process. This maximizes work done by a system on the surroundings. So, you know, even like if you think the stretching of a string, you can think about that as a reversible process as long as the string is, as you stretch it in the elastic region. So you take your string, you apply mechanical strain, you put it under tension, and then if you release it, it will go back to its original. So you're reversing the process. Irreversible would mean that you cannot undo what you've done to it by reversing the change to the system. So let's say if you take a material as sort of a string, but this time you stretch it beyond the elastic part of it. So you stretch it so that you actually put a deformation in it. When you then remove your strain or your tension, it will go back some way, but it will not go back all the way. So you cannot really reverse it. In the same cases where I use that silly example of the Hilux versus the egg, if I drive over the Hilux, if I drive over the egg will crack. If I reverse back over the egg will not uncrack. That, in essence, is what reversible and irreversible processes are. So I'm going to leave it here for this morning, and I'll see you at 12:30 this afternoon. Thanks for tuning in, and see you in a few hours. And there is sunshine out there, so go and stand in the sun for a little bit.